Hello everybody, this is Professor Roman. Welcome to the 10th video in my video lecture series, An Introduction to Discrete Mathematics. Today we are going to discuss logical equivalence, and this is a key topic in elementary logic. Let's take a look at the truth tables for these two simple compound statements. Not P or Q has this truth table, and P implies Q has, in fact, the same truth table. That means that these two statements always take the same truth value. When one is true, so is the other. When one is false, so is the other. And it doesn't matter what the values of P and Q are. So this leads us to a definition. Two compound statements with the same statement variables are logically equivalent if they always have the same truth value for any assignment of truth values to the variables. Whenever two statements A and B are logically equivalent, we'll denote that by writing this expression. So it's the equal sign with 3 bars. And you would say A is logically equivalent to B, or A and B are logically equivalent. So we can now write this. I did say here that the two statements should have the same statement variables. That's not, strictly speaking, required. For example, if you look at these two statements, let's say A is a compound statement that does not involve P, and then we tack on a conjunction with P or not P. P or not P is a tautology. And so this part that is highlighted is always true, and therefore, because this is a conjunction, the entire statement will be true if and only if A is true. So in other words, this is logically equivalent to just A. Okay. So these two are logically equivalent, and yet they don't have the same statement variables. One could make this more formal and describe exactly when it's okay for the two statements not to have the same statement variables, but I don't want to get into that. It's kind of pedantic and not really that useful, I think. So we'll not worry about that. One way, of course, to tell whether two compound statements are logically equivalent is to use essentially the definition and compare the truth tables. The concepts of logical equivalence and tautology, however, are closely related, and that provides another way to check for logical equivalence. So we have a theorem, two compound statements, A and B, with the same statement variables are logically equivalent if and only if this compound statement, A, if and only if B, so it's the biconditional, is a tautology. And the proof is quite straightforward. I suggest you think about this before reading my proof here. The concept of logical equivalence is quite useful. For example, we can use it to describe some properties of the basic connectives. For example, P and Q is logically equivalent to Q and P. Here is a list of properties of conjunction, disjunction, and negation. And when you take a look at this list of properties, you might notice that conjunction compares to intersection of sets. Conjunction of compound statements compares to intersection of sets. Disjunction compares with union, negation with complement. So there are some analogs, some similarities between the properties of the compounds, the conjunctions, conjunction, disjunction, and negation, and union, intersection, and complement. So, properties of tautologies and contradictions. For example, P or C. C is a contradiction. This has the same truth value as P. In other words, this will be true exactly when P is true. And I'll let you look at the rest of these. In fact, you should probably try to sort these out yourself. It's good practice. Idempotent properties. P or P is logically equivalent to P. P and P is also logically equivalent to P. Now, don't make the mistake of saying P and P equals P. That's not true. They're different compound statements, but they are logically equivalent. They have the same logical meaning. We have the commutative properties, the associative properties, the distributive properties, properties of negation, and De Morgan's laws. Okay. And I've left proof of these properties as exercises. De Morgan's laws, as they are in set theory, are particularly useful to clear up some points of confusion in this context. So according to De Morgan's laws, for example, the negation of P or Q is not P and not Q. So or becomes and. Disjunction becomes conjunction. Just as intersection becomes union, union becomes intersection in the context of sets. The negation of P and Q is not P or not Q. So here are some examples in English. It is raining or it is snowing. Negation, it is not raining and it is not snowing. It's surprising how often I hear people mistakenly say in a situation like this, it is raining or it is snowing. Negation, it is not raining or it's not snowing. If you listen to people's conversations, even on television, some news personalities and politicians and others will make these kinds of mistakes. And some other logical mistakes, which we'll come to next when we talk about converses, inverses, and contrapositives. Here's another example. It is raining and it is snowing. Negation, it is not raining or it is not snowing. If these a little bit vague in your mind, I strongly suggest you stop now and spend some time with this until it becomes clear to you, in a sense, I hate to use the term, but in a sense it becomes obvious that to negate this, you would say this. Okay, and similarly down here. This is critical to the basis of logical thinking. So let's look at this now, converses, inverses, and contrapositives, because this is another point of common confusion among, what should we say, lay people, non-mathematically oriented people, or non-logically oriented people. This is the conditional statement, P implies Q. There are three other statements that are related to this one, in some sense, at least syntactically. The converse is Q implies P. So we reverse the roles of the antecedent and the consequent. We switch them. That's the converse. The inverse is formed by just putting negations in front of the antecedent and the consequent. So not P implies not Q. And the contrapositive is to do both. Swap the antecedent and the consequent, and negate both of them. Okay. These are the four possibilities for how you would stick variables on either side of a conditional with or without negation. Okay. So for example, if the sun is shining, then I go to the store, or I will go to the store. Converse, if I go to the store, then the sun is shining. So you reverse the sun is shining, which is P, and I go to the store, which is Q. Okay. The inverse is negate both of these. If the sun is not shining, then I do not go to the store. And the contrapositive would do both. If I do not go to the store, then the sun is not shining. Okay. Now, most of the confusion that I see among students and among non-mathematically oriented types is which of these statements are logically equivalent. Well, it's easy to check with the truth tables. And so I've written one truth table that has all four of the statements in question. And if you look at the truth values for P implies Q, they match perfectly with the truth values for the contrapositive. True, false, true, 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 false, true, true. So a statement, a conditional, is logically equivalent to its contrapositive, but it doesn't match either of the other two. The converse happens to be logically equivalent to the inverse. Okay. The most important takeaway from this, you really should take away this entire table and which is logically equivalent to which. But the most important thing is that a statement is logically equivalent to its contrapositive, but not to its converse. And this is something else that I hear occasionally from people, news people, other types I'm listening to. They will say, in effect, well, since P implies Q, Q implies P. And that's garbage. Okay. So here's a theorem. We have the four statements. A conditional statement and its contrapositive are logically equivalent. The converse and the inverse are logically equivalent. No other logical equivalences hold. And I say in particular, a conditional statement and its converse are not logically equivalent. This should make perfect sense to you. Let's take a look at these examples in English. If the sun is shining, then I go to the store. If I go to the store, then the sun is shining. This does not follow. I can go to the store on a rainy day. Just because I say, if the sun is shining, then I'm going to the store, doesn't mean I may want to go to the store when it's raining. So if I go to the store, it doesn't have to be that the sun is shining. Okay? If I went to the store every single day, it would be true to say if the sun is shining, then I go to the store. It's tempting to read something into that statement that's not there. And what is it that it's tempting to read into it? The converse. Some people will interpret this statement, if the sun is shining, then I go to the store, as a biconditional. The sun is shining if and only if I go to the store. Okay? So they will just, manufacture this idea that this statement implies that if I go to the store, the sun must be shining, and that's simply not the case. Okay. Here's another example. If x equals 2, then x squared equals 4. Since this is true, so is the contrapositive. If x squared is not equal to 4, x cannot be equal to 2. After all, if x were equal to 2, then x squared would be equal to 4. Okay. The converse, however, if x squared equals 4, then x equals 2, is false, because x could be negative 2. And here's the inverse. One of the key uses for the equivalence, logical equivalence between a conditional and its contrapositive, is that sometimes, quite often really, when we're trying to prove a conditional statement, P implies Q, it's often easier to prove its contrapositive. Oops. And so that's just as good, because the two statements are logically equivalent. If one's true, so is the other. In fact, oftentimes, most of the time, when I read a theorem or conjecture an idea that I want to prove, one of the first things that goes through my mind, if it's a conditional, is take a look at the contrapositive and see if it intuitively looks simpler to prove. May or may not be. I may be misled into thinking it's easier to prove. It turns out not to be. But as I say, oftentimes it is. Here's a very simple example. If n squared is odd, then n is odd. Now, this could be proved directly. What does it mean to say n squared is odd? You have to sort that out to prove that n is odd. But the contrapositive is much easier to prove. If n is not odd, then n squared is not odd. Or in other words, if n is even, then n squared is even. Well, there's nothing to that. If n is even, it has the form n equals 2k for some integer k, and so n squared is 4k squared, which is also even. Very simple proof for the contrapositive. So I would suggest spending a little time trying to prove this conditional directly and see how that goes. Here's another situation where logical equivalence is quite useful. Sometimes we're faced with proving a biconditional, P if n only if Q. Since that is equivalent, logically equivalent, to P implies Q and Q implies P, by far, when, the majority of the times when we have to prove a biconditional, it's going to be easier to prove two conditional statements separately, entirely separately, because the statement and its contrapositive are not, its converse are not related logically. So we have to prove both the statement and its converse. There are some cases where a proof of P if and only if Q can be done directly, but they're fairly limited. Most of the time, you're going to have to split the proof into two separate proofs. Proof P implies Q and proof Q implies P. Example. N squared is odd if and only if n is odd. So we have two things to prove. If n squared is odd, then n is odd. If n is odd, then n squared is odd. Statement, conditional statement, and its converse. We've already proven that if n squared is odd, then n is odd. And we did that by proving the contrapositive. So this is proof by contraposition. The converse, however, can be done directly. If n is odd, it has the form 2k plus 1. N squared then looks like this. Whoops. Which is also odd. final point I want to make in this section is that we can do another replacement theorem as we did before. We did one for tautologies. If you have a tautology, you can replace statement variables by compound statements. As long as you do it consistently, you get a new tautology. You do the same thing for logical equivalence. After all, A logically equivalent to B is the same as A if and only if B is a tautology. So I'm just going to read the theorem to you, and I'm going to leave the proof for you. Let A and B be logically equivalent statements, and suppose that A and B contain the same statement variables, P1 through Pn, and possibly others. Suppose that C1 through Cn are compound statements. Then, if we replace every occurrence of Pk by Ck, for all the k's, 1 to n, in both A and B, the resulting statements are also logically equivalent. And the proof takes advantage of the earlier theorem, Theorem 102. So this is a nice, powerful theorem. We know, for example, that P and Q is logically equivalent to Q and P. I can just make up anything I want here. I just replace P by P implies Q and not R, and I replace Q by Q if and only if R, and I get something that looks like this, which is therefore also true, and so the two sides are logically equivalent. If you stared at it long enough, you would see that all that happened was the stuff in the square brackets was swapped. But it's harder to see it here. And this is a very simple example. I could do something more elaborate. This is just to illustrate the idea of substitution for logical equivalence. Okay. I don't know that we're going to have much use for this, frankly, but it can be useful in some situations. Okay, I think we will stop the video. Next is valid arguments, which is, in a sense, why we are doing all this stuff so far, is to get to the point where we can recognize when an argument is logically valid. So we'll do that in the next video. Thank you for watching, and I hope to see you in the next video.